going to present you the evaluation of the intercomparison of the grid formatted products at a global scale that we performed here at BEC. And I want to thank everyone who attended here, especially for the eastern longitudes, which is really, maybe it's late in the day. And also to my co-authors here from BEC, and to Chris Merchant and Peter Cornillon, because part of the results I'm going to present are part of the activities of the Future Fidelity Task Team that I'm co-chairing with Peter Cornillon. I want to briefly introduce you, for those that don't know BEC, the BEC Expert Center on Remote Sensing. It's a working group of the science of the Marine Science Institute, and we are expect support a laboratory for the level 0 and level 2 of the ESA Soil Moisture and Ocean Salinity SMOS mission. And we are currently producing and distributing sea surface salinity and soil moisture products. I want to show you here the motivation of this study. For us, this SST plays a key role in the generation of salinity products. On one side, for the level 2 and level 3, we use it as a ancillary data for the inversion of variety models, and as well we use it as a template to increase the temporal and spatial resolution using multifractal fusion techniques to produce level 4 products. Currently, we are using SST provided by ECMWMF for the retrieval at level 2, or it implies level 3 as well, and the OSTIA SST product as a template for the level 4 product. Here on the graph on the right, I'm showing you the sensitivity of sea surface salinity with respect to the SST as a function here on the SST, and the color represents different values of the sea surface salinity. And as you can see, as we approach to lower temperatures and for lower salinities, this the impact is huge, and then it's really critical for really low salinity and low SST regions, as can be the Baltic or the polar regions. And this motivated us this study to assess which is the best product for us to use. So we will try to answer this question based on the following indicators. On one side, the comparison with in situ data. We will use ARGO, that these are fiducial reference measurements. And we will assess the spectral analysis and singularity. We will use spectral analysis and singularity analysis, to assess respectively the effective spatial resolution and the dynamical properties of the different products. Finally, we'll use the correlated type collocation to estimate the uncertainties of the error for its product. At least we will try. It's not that simple. I don't want to make any spoiler, but you will see. This is the data sets we are comparing. We are comparing these 5 data sets. These 4 data sets, CMC, OSTIA, CCI, and more, are level 4 SST products. So they are giving us the foundation SST, and we use this as a reference. This is the only monosensor product. This is a level 3 and has coarser resolution. This is microwave SST, and so it's giving us a skin temperature. I'm going to hide that. Yeah, sorry. The period that we are going to base for our analysis, we are going to use daily maps for the year 2016. So to begin with, I'm going to briefly show you the comparison with in situ data. This is the spatial distribution of the mean differences between satellite with respect to ARGO. They are ordered from the coarser resolution top on the left to the higher resolution. And our collocation criteria was the following: this in situ center. So that means meaning that for every profile we select the closest SST observation, the closest pixel of SST observation. We just used observations of the ARGO profiles with depths between 3 and 4 meters. I'm showing you here the probability density function with the different statistics. As a first height, they're quite similar, but the CMC seems to provide the more accurate or have slightly lower standard deviation. I'm trying to go fast in that part because I wanted to show you the other that takes more time. This is a summary of the different statistics that I was showing in the PDF. The green shadows indicate the best performance in every statistic, and as you can see, when we consider the comparison with in situ data, our best choices would be between CMC and AMSERI. For computing the spatial resolution, effective spatial resolution, we will use a spectral analysis. And as Reynolds and Shelton showed, the grid spacing of SST analysis is not an indicator of the feature resolution. And this is something that it's still maybe we are getting closer, but it's not that easy to understand among the different users. And I remember Peter Cornillon during the science meeting, the grid science meeting in 2018, he had some troubles to try to convince people and to explain that. So I remember I was there. So we can compute the effective spatial resolution from the power spectral density as the point of the wavelength where the energy drops off from the expected power law. To my knowledge, and if I'm wrong, I would like you to correct me, just a few SST previous works, intercomparison works have explored the spectral analysis. So here we are going to, I will use you for briefly the results we got for these two regions in black here in the Pacific, in the tropical, and the more in the southern. But the results are generic to the other regions. So here we have the power spectrum density. You have it with respect here to the wavelength and to the wave number. And here they are indicating the different colors indicate the different data sets. Now they are ordered from higher resolution to coarser resolution. For those that are not familiar to the spectral density, it's normal that they have these cores have different length, because the minimum wavelength that we can resolve is set by the Nyquist frequency, which is twice the horizontal grid space. So in general, in most of the region, what we see is that the CCI and Moore, here the orange and the green curves have higher spatial resolution when we compare with the other level 4. For comparison, in gray you have the power law expected, the theoretical power law expected for the SST, which is K up to minus 5/3. In general, in most of the regions, CMC and OSTIA, here in red and blue, they don't even, so they have their effective spatial resolution is shorter than the one provided by the microwave, which would be here. In the other graph on the right, what we can see is that here the microwave it's dropping a little bit earlier, and in that case, OSTIA and CMC is giving higher spatial resolution. I'm going to move to the singularity analysis, and I will try to go briefly and be as pedagogic as I can. Let's see. We propose here a new metric. We will discuss in that during the workshop that we proposed at the last science meeting in Barcelona. But for those that you were not in person, so this is the brief summary of my contribution to that workshop. So we propose here the singularity spectrum to assess the structural and dynamical quality of the SST products. And this is based on the multifractal theory of turbulence. Basically, what we have is that in the limit, when the scale tends to 0, we can write the thermal gradients here as the scale up to this exponent, which is the singularity exponent. And this can give us an information of the intensity of the gradients, meaning this exponent, when it is between n and n plus 1, being this n a positive integer, it means that the thermal gradient is derivable n times, but not n plus 1. So this would be the meaning. From this singularity analysis, we can study the statistical and geometrical properties of that exponents that are given by what we call the singularity spectrum. You have here the mathematical definition, but briefly what I want to highlight is that this spectrum can be computed from the probability density function of the singularity exponents. This is a convex function, and what is important is that it's scale invariant, and it gives us a representation of the turbulent cascade. And another important feature to highlight is that this singularity spectrum is the step between it allows us to pass from the canonical, that would be the statistical structural functions, to the microcanonical formalism, which gives us the geometrical information through the singularity exponent. So this is the main features and ideas that I want you to understand. So we have computed for every daily map, and for all the data sets, we have computed the singularity exponents at a global scale. But in order to show you better the differences, I'm just focusing here in a region of the Agulhas of the Agulhas current region, of the Agulhas region. So here you have the cursor. They are ordered as well from cursor spatial resolution to higher spatial resolution, and here the color bar indicates the exponential singularity exponents. The brighter colors, the white, would indicate the most intense radiance, thermal radiance. So here you see that for this given day, we have missing data that may be due to the presence of heavy rain cells. And as well, we have this problem, as you know, that we have with the microwave radiometers, that is the land sea contamination. So I will give you the different results for the other. This is CMC. This is the OSTIA. As you can see, some of the big structures, they are somehow coherent. For the CCI, we are just beginning to have a smaller thermal gradient, and this is the Moore, which combines, and it can give us much more smaller details, but while combining other regions, that these kind of noodles are kind of wider, as you can see here, for instance. So from that, we computed from these daily maps, we have computed the singularity spectrum at the native spatial resolution, and here are for all the data sets. The one that is giving us a behavior much more closest to the theoretical behavior is the microwave data set, which is given here, which is have a more it's close to the convex shape that I was mentioning before. The SST Moore on the other side gives us as well this shape is quite well preserved. But here for the others, and especially for the OSTIA datasets, we have this kind of bump, which indicates that we are kind of losing somehow at a given scale, we are losing energy. So as you can see here with that picture, the higher spatial resolution does not mean that we have a better representation of the dynamical structure or the power cascade, of the turbulent cascade. So as I told you, there is a range of these intermediate gradients here, these exponents, that as it seems that they are being excessively smoothened, and as a consequence, the turbulent cascade is poorly represented. So what we did, we just centered our study now with these two. This is the closest to the truth, let's say, on the left, and for the OSTIA. We want to compute the ratio of days that during this temporal range in 2016 that present a singularity exponent with this band between 0.3 and 0.6, which it's kind of more or less representing this drop of energy. And this will allow us to to see these RT maps in order to find out the regions where these ST gradients are being smoothened. So we should have, as you can see, there are big differences between both data sets, and we are losing, I mean, these gradients are located mostly, as you can see here in the darker, in the intertropical region. So we are kind of smoothing this intermediate gradient. So in order to find out if this is due to the fusion, I mean, to the interpolation techniques or schemes that are used, we have interpolated, since the singularity spectrum is scale invariant, as I told you, we have interpolated the OSTIA dataset to a quarter degree, so to the same scale as the REMS, and we have repeated the same procedure. We proceed in the same way. And this is what we obtain. Now this loss of energy has disappeared, so this is a proof that we have that this loss of energy is caused by the interpolation scheme. We have as well repeated now the maps of the ratios, and now you can see that these two maps are much more in accordance. So here, with that, we can conclude that this is it could be a validation tool of the consistency of the dynamical control of the different SST products. And last but not least, I want to briefly introduce you the correlated triple correlation. I'm pretty sure that among the community you already know the triple correlation. It's been widely used to assess the quality of many geophysical variables, but acquired with different instruments and at different temporal and spatial scales. But here our focus is in the error characterization of remote sensing maps that having 3 different collocated data sets completely independent is quite unlikely. So for that reason, we have developed a new formulation that we call the correlated triple correlation for the case that we have 3 data sets that resolve similar spatial scales, being 2 of them having correlated errors. And this allows us to characterize the quality of different data sets at each location, so we can provide a map of the standard error distributions. So here briefly I show you the rationale of the methodology of that methodology. I'm not going to enter into details. I will refer you to the paper. But basically, we want to estimate the standard error deviation of the error delta E, and we do these 3 assumptions. We assume that the errors of 1 and 2 are correlated, but uncorrelated with the third data set. These 3 data sets, we assume that they are resolving the same spatial scales, so we don't have any representative error. And we do as well assume that the intercalibration factor will be this coefficient here. It's equal to 1. We assume, and we have proved that as well. So this methodology allows a reliable estimation of the errors, having scarce sample sizes. With 1 year of data, we can provide the maps. But what happened when we try to apply this methodology to the different level 4 products? That it's almost impossible to find any combination of triplets of 3 data sets that are uncorrelated one from the other, because they are using mainly the same sensors. So it was kind of a problem. So the approach we came to is that we realized that only 2 data sets are having information from SSMI sensors. So we will assume that these 2 data sets are uncorrelated, are the uncorrelated one with respect to the other. And this allows us to perform these different templates. So the errors of the sensor will be computed as a part of the SST variability, and we will be able to obtain 3 different estimations, 1 per triplet, of the standard deviation of the SSMI sensor for each data set. So in order to ensure that all data sets resolve the same scales, the spatial scales, we have interpolated all the data sets to the same grid, to the cursor grid at 1/4 the grid. And with that, now we are ready to run this tool. So how we did proceed? As I told you, we will have 3 different estimations for 3 for Moore and 3 for OSTIA. And for that, normally what we do, we have many triplets and we give the final result as the meaning of all the realization. But since here we have only 3 triplets, what the procedure that we follow is the following. From these maps, we compute a map with the maximum error here. I mean, in every pixel, we take the maximum error and the minimum. And by comparing these 2 maps, by making the difference, we are going to be able of having quality of the estimations, which is that. So here you have the same map as before, but with on the left you have the probability density function, and this would be it will give us an indicator of the uncertainty of the uncertainty. So as you can see, there are regions that the spatial patterns that appear are kind of I don't know, shocking. I guess, and I assume, and I would like to ask it to the community, this is one of my questions to you. I guess this is due, and it reminds me the transects that maybe of the in situ data of the transect sheet that maybe they are being assimilated in one of the analyses. So given that uncertainty, we just can provide a map of the standard error of SSMI sensor in the regions that will be, let's say, we will put like a threshold, and we will give that map in the region that are between 0 and 0.3 degrees. So we did the same for the OSTIA sensor, and as you can see, they are different, the amplitudes are different, but the spatial structures are kind of the same, let's say. And so finally, this would be our estimation of the standard error of SSMI provided by OSTIA, and on the second row by Moore. The bluish points is the points that we mask out because we consider that we don't have the estimation is like the uncertainty of the estimation it's higher. So these, as you can see, there are as well differences, but they are kind of coherent. You have here the probability density function, and as you can see, the statistics and the metric, we could say that the standard deviation of the SSMI error, it's about 0.3 and 0.4 Kelvin, so degrees, that it's in accordance with this in situ assessment. I hope that with that we can show you that the CTC is a powerful tool for estimating the standard deviation of the errors and providing its spatial distribution, and this can give us some hints of the source of the error, if it's land sea contamination, RFI, or maybe some due to the atmospheric corrections, etc. So to sum up, as you have seen, choosing the best L4 SST analysis is not an easy task. Greece is providing now users with some guidelines that you have here, the reference. As I hope I have shown you, as you can see, the comparison with respect to the in situ data does not give the global picture, and we are proposing here a new metric in order to assess the SST products from a dynamical and a structural perspective, which is the singularity spectrum. We have also shown the potential of the correlated intercorrelation for estimating the standard deviation of errors and providing the distribution of the spatial distribution of the errors. So our final our final election and our answer to after seeing this analysis is that we will use the Moore level for SST product, but at its effective spatial resolution that we estimated it's 1/10 of degree. We are currently retrieving the sea surface salinity using this product in the southern ocean, and so we need to assess the impact of this new SST retrieval. I hope that my colleagues and I can give you some updates on that in the following meeting. As further work, I think that further errors should be addressed to characterize the effective spatial resolution for smaller regions, maybe at a global scale, because as you know, it's not going to be homogeneous. I mean, the products are not going to have the same spatial resolution in all the globe. So I think it would be nice for the users to know which product is best in each region. We would like to use the CTC at level 2 to characterize the standard deviation of the errors for the different sensors. But this is depending on the available resources and maybe mid, long term, I don't know. I think we will need to understand further what is needed to understand which methodological choice of the producers have higher impact on not preserving the expected singularity spectrum. And for sure, as a recommendation to Chris community, I think we need to improve the interpolation and fusion scheme to respect the turbulent cascade. And these are the reference I was just mentioning during the presentation, and that's all on my side.